Welcome all. The topic is addressing modes of Intel 8086 microprocessor. So what do you mean by an addressing mode? Addressing modes are different ways in which a source operand is denoted in an instruction. Take an example of an instruction in 8086. Say move CL, 12H. So move stands for move instruction. It will move the data from the source to the destination. So which is source and which is destination in move CL, 12H? In the 8086, after the opcode like MOV, whatever is the instruction name, the destination immediately follows it. So in this instruction, move CL, 12H, CL is the destination. Then after that, there is a comma. After the comma, you will be specifying the source operand. So move CL, 12H. That means the data 12H will be moved to CL. So here the source operand is 12H. Now I repeat, addressing modes are different ways in which the source operand is denoted. So in this given example, move CL, 12H. Which data has to be moved to the destination? It is 12H, and that data is given immediately in the instruction. It is immediately available in the instruction. You don't have to go anywhere. That whatever data you need to move to the destination, it is directly given. So there are like this. So this is only one type of addressing mode, which is immediate addressing mode. Like that, there are 8 different types of addressing modes, which we will be seeing in the coming slides. First one is an immediate addressing mode. So in this mode, the operand is specified in the instruction itself. If you see the first example, move CL, 12H. What is the capacity of a CL register? It is the lower half of CX register. As you know, all the registers of 8086 are of capacity 16 bits. So CL will be the half of CX, lower part of CX, that is CL. So CL will be 8 bits. So we can take a 12H. That will be a total of how many bits? 8 bits. Because it's a hexadecimal, 2 will take 4 bits. Again, 1 also will be taking 4 bits. So that will be moved to CL. This instruction will move this 12 immediately into the CL register. So after this execution is performed, your CL register will be having the value 12H. So which is the source operand in this instruction? Move CL, 12H. The source operand is the second one. In this case, it is 12H and it is moving to the destination, that is CL. So addressing mode is the different ways in which source operand is designed or defined in the instruction. So in this case, as you can see, the source operand is immediately available. It is the data itself. That's why the name immediate addressing mode. So second example, add AX, 2387H. So this instruction, what it will do is, it will add the value 2387 immediately with the contents of AX and the sum will be stored in AX. So here also the source operand is 2387H, which is immediately available, and that's why the name immediate addressing mode. The second one is register addressing mode. Now you may guess what it will be, because for an immediate addressing mode, the source operand was an immediately available data, the data itself. So in this case, the data will be available, the source data will be available within a register, and that register will be defined in the instruction. And few restrictions here. it's important for instructions to use the registers that are of the same size. And your CS register should not be the destination register. And this register will be one of the fastest executing of all the addressing mode instructions. Why? Because registers, the system won't take much time to take the data directly from a register, because registers are immediately available to the execution unit of the microprocessor. So an example here for the register addressing mode, move CX, AX. So what it will do, it will copy the contents of the 16-bit AX register into the 16-bit CX register. Can we give here move CL, AX? AX is capacity of 16-bit and you know CL is of 8-bit. There is no matching between the source register and the destination register, so that instruction is wrong. So there should be a matching between the source register and the destination register. Similarly, we can go for add instruction, add BX, AX. This instruction adds the content of AX with the contents of BX, and the sum will be stored back to BX. So there will be contents in BX as well as in AX. That contents will get added. The sum, the result, will be stored back to BX. The old value of BX will be overridden with the sum of AX and BX. Next is direct memory addressing mode. Here, instead of giving the value, instead of giving the source value directly, we will be telling about the memory location where that value is residing. That's why it's called direct memory addressing mode. So what is the type of address we give in this instruction mode? That is the offset address. You know, 8086 follows the memory segmentation, which gives it the ability to address 1 megabyte of memory by using 16-bit internal capacity. So an offset address will be given. Example here, move CL, 4321H. So what's the difference between the format of this with the format of an immediate addressing mode instruction? You can see a square bracket enclosing the source operand. The data is enclosed with a square bracket. In the immediate addressing mode, there was no square bracket. If we give here move CX instead of CL, move CX, 4321H, that 4321H value will be moved to CX. Why I am telling about CX? Because 4321H is of capacity 16-bit, which cannot be moved into CL. So if I remove this square bracket, this instruction will be wrong. It will be telling there is a mismatch. The system won't be able to assign 4321H, which is of capacity 16-bit, into a 8-bit register called CL. But in this case, move CL, within bracket 4321H, the content of this memory location will be moved to CL. And 8086 follows a byte addressable memory. When you have an offset address, when you have a physical address, from that address only 1 byte of data can be taken. Each byte of the memory is addressable, or each byte of the memory is having separate physical effective address. That's why it's called byte addressable. So this data which is residing in this offset address of 4321H will be moved to CL and not the value 4321H. How will you calculate the physical effective address? It is by default, you know that it's an offset address, it's a value. So the physical address will be calculated as DS into 10H plus 4321. Why? Your data segment register marks the beginning of the data segment, where somewhere in that data segment this address is residing. 4321H offset address is residing. So from the beginning we have to move an offset of 4321H. Then only you will find that data, and that data will be moved to CL. Why we are multiplying 10H to the value of DS register? That is for that left shifting by 4 bits, which we have already discussed while we discussed the architecture of 8086. We are left shifting the DS register value by 4 bits in order to make it a 20-bit address. So with that 20-bit address, this 4321 offset address will be added, and we are getting a resultant physical effective address as 54321H, which is of 20-bit address. The value residing in that memory location will be moved to CL. The fourth one is register-based indirect addressing mode. From the name itself, it is indirect. In your previous case, it was direct addressing mode. We had a clue from which address or which memory address you need to take the data, because that address was directly given in the instruction. But here it is kind of indirect addressing. That direct address is not directly given in the instruction. Instead of that, that address will be residing in a register, and we will be specifying that register as the source operand. So if register is SI, DI and BX, then the segment register will be DS by default. If base pointer or stack pointer, then SS will be the default segment register. All these things are for calculating the physical effective address. Here, first example, move CX comma BX. If it was without bracket, it would have been a register addressing mode. But here I am enclosing my source register name with a square bracket. That means it is indirect. So what is inside that BX? The BX contains not the value here. The content of BX will be the address now, since it is enclosed within that bracket. Find the difference. If I was just writing CX comma BX, the content of BX will be considered as the data, and that data will be taken directly and give to the CX register. But since I have enclosed the BX register with a square bracket, that means the content of BX register is an address and not the data. So we have to go to that particular offset address. We need to find out, calculate the physical effective address as per that particular offset address. And that we have to go to that location. We should find out what data is residing in there. That data will be moved to CX register. So you know that your CX, it is byte addressable. Your 8086 is byte addressable. So if you go to that effective address of BX, whatever it is, we will be getting a memory location. Since it is byte addressable, we will be how many bits we can extract from that memory location? We can get only 1 byte. Other words, 8 bits of data. But we are trying to put that 8 bits into a CX register. CX register is but of how much capacity? CX register is of 16 bits. Now there is something happening in the background. Your first BX value, whatever is the value you are getting from that location, calculated by the BX register value offset, that will be moved to CL. 1 byte of data, that will be moved to CL. Now what happens to CH, which is also a part of CX register? That CH value, for that what we will do is, whatever is the offset value in BX, that will be added with 1. And that one will be used for calculating the effective address with respect to the data segment. And that value, we will be getting again one more address, the next consecutive address. That value in the next consecutive address will be moved to CH. So it is like DS into 10H plus BX, and for the next one, it is DS into 10H plus BX plus 1. So that is register based. The fifth one is register relative addressing mode. In this mode, the operand address is calculated using one of the base registers or index register and an 8-bit or 16-bit displacement. we have two input parameters here. We have a register and also we have a displacement. We need to consider two things before calculating the physical effective address. For example, move CL comma, within bracket I have two things. One is a base register, another one is a displacement. So this instruction moves a byte from which address? Pointed by bx plus 4 in the data segment. So how will you calculate the effective address? ds into 10h plus bx value plus some 4h, whatever is the displacement given. So that will be the physical effective address. That value will be picked up and that will be given to the CL register. For a single effective address, you will be getting only 1 byte of data. So it is perfectly fine to move that 1 byte of data to a CL register, which is again of capacity 8 bits. So here the operand address is calculated as base register plus an index register. Unlike the other one, in your previous case, register relative, you had two parameters. One was the base register, another one was the relative address which was immediately available. Here you have base register and an index register. Instead of directly giving the displacement, you will be giving that displacement in SI register. So here the effective address will be ds into 10h plus bx plus SI. The seventh addressing mode is relative based indexed addressing mode. So in this mode, the address of the operand is calculated as the sum of base register, index register and an 8-bit or 16-bit displacement. You have three parameters to decide or to calculate the physical effective address of the source operand. And it's often used to address a two-dimensional array of memory data. We will see how in the next slide. So this take an example for this relative based index addressing. Move CL comma bx plus di plus 20. So this instruction moves a byte from the address pointed by bx plus di plus 20h in the data segment to CL. A practical application for this. Suppose you have a file of many records exist in the memory and each record contains many elements. You have a file of many records and each record contains many elements. It is like a two-dimensional array. If you think of, you can think it of as a two-dimensional array. So the displacement can take you to where that file is residing in the data segment. You have reached that particular point. Now the base register will addresses a particular record within that file and an index register will take you to a particular element within that selected record. So it is a very useful addressing mode. The last one is implied addressing mode. In this mode, the operands are implied as the name suggests and hence not specified in the instruction. By seeing the instruction itself, the 8086 will understand what to do with that instruction and what is the source operand. CLC, first example, it will clears the carry flag. You don't have to give CLC and followed by the carry flag register. Or the carry flag, as you know, you have a flag register and one of the bit is for denoting the carry of that particular previous execution. So if there is a carry generated, your carry flag bit of the flag register will be set to 1. If it is already set to 1 and before some particular execution, you need to clear all your carry flag setting within that flag register. You have to clear the carry flag bit of the flag register. You can just type CLC. No need of any source operand. That's why it's called implied. Similarly, you have XLAT, which stands for translating. You don't, it is basically to translate the contents of an AL register. And here also you are not specifying XLAT followed by AL register, because system, it is implied that the source operand or the register in which that XLAT has to be applied is the AL register. So that's all about the addressing modes of 8086. Thank you.